to do proof logging for symmetry wrecking. Please.
Thank you very much. And yeah, specifically, I'm going to talk about symmetry wrecking for SAT. So I'm going to talk about the Boolean satisfiability problem, which we, I think, all know is given a Boolean formula f in conjunctive normal form. Is there a satisfying assignment to the variables of the formula? And of course, this problem is very, very important, both in theory and in practice. And it's in fact so interesting in practice that there has been this decades-long effort by the SAT community to develop faster and faster SAT solvers. And so what this is showing is the SAT Museum. And so there's a yearly competition of SAT solvers where the fastest algorithms go head to head to find out which is the best algorithm. And this figure here shows the winner of each year on a fairly recent set of benchmarks. And what this basically shows is that the SAT solvers are getting faster and faster and faster, so that this effort is actually working, and we're getting more sophisticated algorithms almost each year. And if you look at the very top of this table here, you can see that there is KISSAT. KISSAT is the current pinnacle of SAT research, and it's a highly sophisticated tool, and it's also really useful in practice. So you can do hardware and software verification with it. You can do mathematical research. If you get stuck on a Sudoku, you can use KISSAT to help yourself out. So it's a really sophisticated tool, and it's very useful. Now, this is the pigeonhole principle. And the question is, do pigeons fit into n-1 holes? And okay, the figure sort of suggests that it's possible because there's two pigeons up here, but the point is that one hole is supposed to only fit one pigeon, and the answer is, of course, no. N pigeons do not fit into n-1 holes. But we can also consult a SAT solver to confirm this. So we can model this into SAT and then ask KISSAT, do n pigeons fit into n-1 holes? And if you do this, it turns out that this is actually not a simple question, but well, since KISSAT is taking so much time to answer, it must be the case that it's actually a very tough question to figure out whether 15 pigeons actually fit into 14 holes. Okay, of course, there's something wrong here, and I think there's different opinions of what is wrong. So some people may argue that this is actually user error, and I've encoded the problem badly, and I should have encoded it differently such that the SAT solver can handle it. Kieran may say, oh, you should formulate this as a CP with all different constraints, and then it would also be obvious. But I think actually the instances contain everything that you need to solve them efficiently. And namely, that is the symmetries of the formula. So you can solve the pigeonhole principle with a symmetry argument. All of the pigeons are symmetric. All of the holes are symmetric. So by symmetry, pigeon 1 goes to hole 1, pigeon 2 goes to hole 2. And this also exists in this CNF form. And so this talk is going to be about symmetry, and usually I talk about symmetries of graphs. So this is, I think, a natural language for symmetry, and a symmetry of a graph is a permutation of the vertices of the graph such that the edges go to edges and the non-edges go to non-edges. And I will talk more about why I'm talking about graphs in a second. Now, importantly, we have efficient practical algorithms which compute the symmetries of a graph. So there's implementations which, given a graph, can fairly quickly tell you, oh, these are the symmetries of that graph. And my main work is in these kinds of algorithms that actually compute these symmetries. And during this talk, I will use a little bit of symmetry language because I will need it. And so one important fact is that the symmetries of a graph, they form what's known as a permutation group, and you can efficiently represent this permutation group using generators. And what does this mean? Well, if you have a symmetry and you have another symmetry, you can compose them and you may get a third symmetry. And a generating set for such a permutation group is a sufficient set of symmetries such that by composing them exhaustively, you can get all of the symmetries. So it's like a smaller representation of all of the symmetries. Now, another more detailed thing that will be important much later in the talk is that we can also talk about the support of a symmetry. So symmetry is a permutation. A permutation may not actually move all of the points of the domain. It could be much smaller. It could only move a couple of points. And what the support says, well, it just contains all of the points that are actually being moved by the symmetry.
Press the camera button twice again.
And yeah, so what the support basically tells us is the encoding size of a symmetry, because we only need to remember the points that are actually being moved. All right. So what does this have to do with SAT? Well, we can also represent the symmetries of a CNF formula as a graph. So given a CNF formula F, we can construct, so first of all, we can define what is actually the symmetry of a CNF formula or syntactic symmetry. And the syntactic symmetry is just a permutation, bijection of the literals, which maps the formula back to itself and also preserves the negation in the right manner. So if some literal L gets back to some literal L prime, then not L must go to not L prime. And we can model this as a graph. So here's an example formula. And the way we model this as a graph is we take every possible literal and turn this into a vertex. Then we connect the two vertices corresponding to the same variable by an edge. And then we just encode the clauses by adding vertices to the graph representing these clauses. So for example, this first one, B1 or B2 or B3, it becomes this vertex down here where the vertex gets connected to the contained literals of the clause. And if you look at this formula, you can fairly easily, I would say, spot that there is this symmetry exchanging B1 and B2, and this symmetry also exists in the graph. So here we exchange the vertices corresponding to B1 and B2, and in fact, with this construction, the symmetries of the graph are precisely the syntactic symmetries of the formula. And if I talk about this slightly more generally, this doesn't just work for CNF formulas. If you have some finite relational structure, you can take this and efficiently model it as a graph such that the symmetries of the graph correspond to the symmetry of the relational structure. And this is sort of the wrong way round, right? You take a very expressive object and you can efficiently model it as a graph. That's maybe slightly surprising that this works and also works efficiently, but this is why we usually talk about graph algorithms when we talk about symmetries.
If you do this in practice, would you somehow make sure that the closed vertices and the variable vertices are different?
Yes.
Or would you just add a couple of dummy extra edges or something? Or no, they're like different type of vertices? Or
yes, so these are so usually we represent exactly this as colors. And so this is why these clause vertices are colored differently from the vertices. In theory, you don't need colors. You could do this by attaching small gadgets everywhere and all of this. But in practice, we use vertex colors to represent this distinction. All right. Oh, now we have the symmetries of a CNF formula. Now we want to use it to solve SAT faster in some way. There's many ways of doing it, and I'm mostly going to explain one of the ways of doing it, but many of the concepts transfer to other ways of exploiting symmetry. Now, okay, and the way I'm going to explain this is by pretending like we have a really bad algorithm for SAT. But let's say we want to solve this formula x and y and z. This is of course trivial to solve, but let's say we have this very trivial algorithm which just goes through all possible assignments to these variables. So we just enumerate all of the possible assignments and we test each one in the formula, and if one of them succeeds, we know it's SAT. If none of them succeeds, we know it's unsat. Now the observation with symmetry is that, well, if we have an assignment sigma and we have a symmetry phi, then actually f under sigma must give the same value as f under sigma composed with phi. In other words, if we have an assignment, we permute it with a symmetry, that permuted assignment must give the same result. And using that, we can look at all of these assignments and basically look at the equivalence classes under symmetry. So in each box, we can permute all of the assignments to each other via symmetry. And the observation tells us that actually we only need to test one of each case. So we only need to choose one canonical representative per orbit or per isomorphism class of assignments, and this suffices to test for satisfiability. And okay, so the specific technique I'm going to talk about is called static symmetry breaking, and what we do there is we add clauses that falsify non-canonical assignments. So we add some clauses to the formula which forbid some of these non-canonical assignments. And the way we usually do this is with a lexicographic ordering. So here the canonical representative is actually the smallest string when you look at the lexicographic ordering. And so the ones that we forbid are the non-minimal ones, essentially. And for example, this constraint here is another way of phrasing this is x is less or equal than y. Now, there's two different ways. I talked about user error before. There's generally two ways of adding them. Either you can add them manually, which is often done in SAT, which is why I said I could have solved the pigeonhole principle by being smarter and adding these myself. Or there's also automated tools to compute them. But since the main point of this talk is going to be correctness, I think the correctness applies to both. So whether you add them manually or you add them with an automated tool, you would like to make sure that they're correct and have proof of correctness. All right, I want to take a little bit of a closer look at what I just showed you, like the static symmetry breaking. And actually what I did was that I first defined a total ordering over the variables, because I just started to write these as strings, right? But in order to write them as strings, I actually need to order the variables somehow. So I chose some total ordering over the variables, and then I treated these assignments as strings according to this total order. And then I chose the lexicographically smallest assignment to be canonical. So there were some implicit steps, and when we later go to the proof logging, these are actually explicit steps, because in order to argue this to be correct, we need to have an explicit notion about these orders. Now, to rephrase the static symmetry breaking in slightly more generic terms, so if we have a symmetry phi, the constraints that we're actually adding, they're basically comparing the current assignment lexicographically to the assignment permuted under symmetry. So basically what this is saying, the current assignment has to be smaller or equal lexicographically than the current assignment permuted under the symmetry. And yeah, the way we precisely encode this is going to be on a later slide. Now, thinking about this for a second, if this constraint is actually conflicting, so if we have an assignment which leads to a conflict in this constraint, then this means that we can take the current assignment and map it with the symmetry to a lexicographically smaller one, basically saying we should be looking there instead. But the current one is not the lexicographically minimal one. Instead, we should be looking at this smaller one instead of the current one. Now, actually, I think it's not even clear that these constraints here should help the solver. So it's not clear that adding these constraints will help the solver to be faster. And in fact, it's sort of obvious that we cannot produce all of them. And if you play around with this, it's actually very easy to add constraints which actually slow down the solver. So, okay, adding all of them is infeasible. A lot of choices are bad. So there's some design and engineering work which goes into choosing the correct constraints and constraints that actually help the solver. And there's somehow an overhead versus benefit thing going on, because we should not be adding too many. We should only be adding the ones that actually help the solver. And now, of course, this is what you think about when you actually design a tool which does this automatically. And there have been a couple of tools that have been specifically developed for SAT. So the first implementation is probably due to this fairly old paper now by Crawford, Ginsberg, Lux, and Roy. However, this was this was not a very efficient implementation, and I think it also had some issues. And then later Shatter came along, and it basically implemented these algorithms from the earlier paper much more efficiently. So it was actually feasible in practice. Then more than a decade later was Break It by Judith Rindt and Bart Bochertz, which had various improvements. Then more recently, this was also the first tool where proof logging was actually added to the tool. And then last year, together with my colleague Sophia Brenner and Laura Fratan, I developed this new tool called Satsuma, which improved over Break It with some new stuff. And okay, in my abstract, I promised to talk a little bit about these symmetry breaking algorithms, and this is why I'm going to show you two small details about what these improvements actually are. And a thing that's really important in these symmetry breaking algorithms is to not just add symmetry breaking constraints ad hoc, but to first go and try to understand the group better and try to find structure in the group such that you can actually choose the symmetry breaking constraints in a meaningful way. And a structure that has been around for a while is this row symmetry. And row symmetry is actually fairly simple. It means that you can arrange your variables in such a matrix shape, and row symmetry means that you can exchange the rows arbitrarily via symmetry. And now, why is this structure so interesting? Well, it's interesting because we know how to treat it perfectly. So there's this this result has been around for a while, and we know how to make efficient complete symmetry breaking constraints for rows. And this has also been used in automated tools. So Break It implements this detecting this row symmetry, and it's also heavily used in mixed integer programming. So if you run skip, it will also try to detect this row symmetry and exploit it. Now, one thing that we improved, in particular over Break It, of course, is that it's not so easy to detect row symmetry efficiently. And in particular, these SAT instances, so CNF instances, can be very, very large. So SAT competition instances can be multiple gigabytes. And so actually doing this efficiently is not so easy. And so we implemented more efficient algorithms to detect this row symmetry. But we also detect more generic structures. So there's also row column symmetry, which is you have a permutation of the rows and of the columns. And so basically pigeonhole principle, when you think about it, is actually row column symmetry, because there's the pigeons that can be permuted and there's the holes that can be permuted. And we also detect what we call Johnson symmetry. It's a little bit more involved, but you can also, I mean, I draw this weird graph here. You can also think about the Peterson graph if you notice. And so basically the variables correspond to edges in a complete graph. And so basically the permutations of the variables, they correspond to permutations of this complete graph. And this is natural when you encode problems asking for the existence of a graph, for example. And yeah, so for these, we don't have complete symmetry breaking constraints, but we have fairly good ones. Also, a different thing that I want to mention here, but I only talk about static symmetry breaking, but actually, even if you do dynamic symmetry breaking or anything more involved, identifying the group first will help there as well. Because in particular, the row symmetry, since we can treat it so easily, you should handle it differently from, say, symmetries that are not of this shape. Now, okay, Satsuma can recognize these, and it can also do simple combinations of these groups, which start to become more messy, but they do in practice. Okay. So the question, of course, is, does this work in practice? Can you actually use this? Coming back to the pigeonhole principle, if you run Break It, this does work. So there's a huge gap of runtime between KISSAT and Break It with KISSAT, but it does not really work at scale. And this is this not so efficient implementation of the row symmetry detection. And so with Satsuma, this scales much further. So Here the formulas are already multiple gigabytes and it's still below 2 minutes, I think, so it's no problem. Although I've just heard that Satsuma stops working around 5 billion clauses or something, then it crashes, but it does scale much further. And okay, pigeonhole principle is not interesting, I've said this myself, but you can also apply the, so it's Satsuma you can also apply in general, and on the 2024 set of sub-competition instances, we could roughly observe a 13% improvement in the part 2 score against normal KISS-SAT. Okay, of course there's a big catch here. We all know that SAT solvers are certifying algorithms, but these results are all not certified. So these are all without proof logging. We didn't check our results. This is just running the algorithms with no proof that they're correct whatsoever. Okay, we talked about certifying algorithms all day, so you know this. A standard algorithm gets input, produces an output, and a certifying algorithm also produces a witness, which together with the input and output go into a checker, and the checker accepts the result or it rejects the result. And these certifying algorithms are, of course, a preferred kind of algorithm. It's better to have an algorithm that checks their work. In particular, if the checker is formally verified, we can get formally verified answers. And of course, proof logging is a slightly more specific version of this, where the witness is produced using only a couple of print statements, which is at least the idea. And of course, we would like to have this for these symmetry breaking clauses as well. We want to be able to prove them correct. Now, actually proving these symmetry breaking constraints correct is not so easy. And in fact, doing this in full generality has not been around for long. So the first time this was actually possible was in this work by Bart Bauchatz, Stefan Goch, Kieran McCreesh, and Jakob Nordström in the VeriPB system, and which is of course why I'm talking about this. And yeah, I want to explain a little bit about how this works, but I want to stick more to the intuition and the important proof rule that is necessary to prove symmetry correct. Now, importantly, the proof system has a notion of orders over assignments. And when I say this, you should immediately think about this lexicographic ordering that we used for these symmetry breaking constraints. So we had this this order over the assignments, and we wanted to say that, oh, we only want the smallest one under symmetry. And this is why this notion of orders will help us. And what we're going to do is we're going to pretend like we solve an optimization problem with respect to this order. Now, of course, we're solving SAT, which is not an optimization problem, but adding this is okay, right? Because we just want any assignment. If it also happens to be the smallest assignment under symmetry, that's fine, right? So it's okay to pretend like we're solving this optimization problem. Now, okay, there's a technicality here that will be important later, which is that we actually define this order ourselves. So we use pseudo-Boolean constraints to actually define what it means for two assignments to be smaller or equal. Now, the way we do this is that we write this as a particular constraint. So for example, if we have two assignments, X and Y, and we want to define what it means for X to be lexicographically smaller than Y, we can, for example, write this exponential sum here, where the most significant bit of our assignment gets the largest coefficient, and the less significant bits get the smaller coefficients. And so we can define what it means for two assignments to be lexicographically ordered using such an exponential sum. And this will be important in a bit. Now, we can then say that we load this order over some set of variables, and once we've loaded this order, then we are in this optimization problem setting where we can start to argue using this order. And yeah, so now we come to one crucial detail that will be super important for us to be able to derive multiple symmetry breaking constraints, which is that VeriPB actually distinguishes between the constraints that we start with in the original formula and the constraints that we derive ourselves in the proof. So there's a set of core constraints, which is the original formula, and there's a set of derived constraints, which is the constraints that we added in the proof. And so in the beginning, we start with only the core constraints, and then when we make derivations in our proof, we start to add things to this derived set, but they stay over here. So we can always distinguish them. And there's a particular invariant that is kept during the derivation of the proof, which is that if we can ever satisfy the core with an assignment, then we can somehow change this assignment with a witness substitution omega such that we can satisfy both of them. So any assignment that satisfies the core, we can fix up in some way to satisfy both of them. But we can fix it up in a very specific way, namely in a way that doesn't make the order worse that we've loaded. So we have this ordering over some set of variables, and the invariant actually tells us, well, if we can satisfy the core, we can satisfy both. And while we're fixing the assignment, the ordering doesn't get worse. Okay, now why will this be important? Well, this will be important because our symmetries, they're symmetries of the core. They're not symmetries of the derived set. So when we add things during the proof, we may be messing up the symmetry, because the symmetry is very delicate. When we attach somewhere in the formula something, this will probably ruin our symmetry. And so this is important. That's why it's important to be able to separate between the two, because this delicate symmetry only lives on the core constraints. Okay, now how can we actually derive the symmetry breaking constraints? And the rule that we're going to use for this is called the dominant space strengthening rule. And what it says is that we can derive a constraint C, which will be our symmetry breaking constraint, if the following hold. So there is a witness substitution omega. Of course, this will be the patching up part. And we have cutting plane proof that the following holds. Now, okay, I want to go through this slowly. What is on the left side, what is on the right side. So what it says is, if we have an assignment which satisfies the left side, so it satisfies the core and the derived set, but it does not yet satisfy the clause that we're adding, then we can fix up the assignment such that the core constraints are satisfied. And, well, what does this mean? It just means that the ordering gets strictly smaller. Okay. This may look weird at first, because the invariant actually says that we need to be able to fix up the core such that the derived set is satisfied again, and what we're adding here must also be satisfied at some point, right? Because we're adding it to the derived set, so we must give proof that we can fix up the assignment to also satisfy this new clause. Okay, so this is somehow weird. C does not appear on the right-hand side, and the derived set does not appear on the right-hand side. And yeah, so why is this correct? Okay, so here's a sketch why this actually suffices. So let's say we have an assignment which satisfies the core and the derived set, but our newly added clause is not yet satisfied by this assignment. Well, then we know that we can find a strictly smaller assignment, which is what this part on the right here says, which satisfies the core constraints again. So now we have this alpha prime, which satisfies the core and is strictly smaller than what we've started with. By the invariant, so by this invariant that we can satisfy the core, we can also satisfy the derived set, we can find less or equal alpha prime prime, which satisfies the core and the derived set again. And it's important that while we fix up the assignment, we are not actually making the ordering any worse. Now, if this still does not satisfy the clause, so if it satisfies the clause now, then we're done. But if it does not yet satisfy the clause, then we can just repeat the argument. And we are back on the left side. We can just apply the thing again, get a strictly smaller assignment which satisfies the core again, meaning we can satisfy the derived set again, and we can repeat the argument over and over again. And the observation, of course, here is that we actually have a finite ordering over the assignments. So eventually we reach the smallest we reach the smallest assignment, and at this point, this must stop, and meaning we must have found an assignment which actually satisfies the core, the derived set, and the clause. All right. Now, why does this help with symmetry? Yes. So how can we actually derive these symmetry backing constraints with this? Okay. Yeah. For this, we need to observe that our witness is the symmetry. So this omega here, this just will be our symmetry, permuting the core back to itself. Meaning that immediately we know that the core equals core under our symmetry. So this implies this direction. Now the clause that we're adding, it actually encodes that the ordering is less or equal to the ordering under our witness. This is what the symmetry breaking constraints were to begin with. So we're just adding a constraint which directly encodes this. Meaning that if we take the negation of this clause, this just encodes that the ordering gets strictly smaller. So if this is not satisfied, then under the witness, the ordering will be strictly smaller. Which means that this part here on the right-hand side is also immediately satisfied. So, so this means that this dominance rule just does exactly what we need to derive these symmetry backing clauses. It just fits perfectly, and it follows almost directly from the properties of the symmetry backing constraints and the symmetry that we use to derive it. Now, crucially, of course, when we derive this C, it goes into the derived set, meaning that the right-hand side here actually does not change, meaning we can do this over and over again, and we can actually derive many symmetry breaking clauses using this rule. Oops. Now I want to only briefly flash some very PB code, and the only purpose of this is to show you that what I've talked about here just immediately maps into the practical system. So in actual very PB syntax, we first define what, for example, a Lex order is, and for this we use some proof rules which define an ordering. So here we are defining what it means to be a lexicographic ordering over 3 variables, and for this we get some fresh variables, and then, for example, we write down this exponential sum over the variables, and then, okay, we need to prove that what we've defined is actually an ordering. So we need to give a proof of transitivity, also of reflexivity, but here this can be auto-proven. And once we've defined this ordering and proven that it actually is an ordering, we can actually load it. So we can load it over a set of variables that are in the input. And once we've loaded this, we can argue using the ordering. And for example, here we derive a constraint by dominance. And what this constraint here says is that x1, x2, x3 is lexicographically less or equal than x2, x1, x3. So there must be a symmetry exchanging x1 and x2. So we can just derive this via dominance. It almost follows automatically. There's some small things that you need to do by hand. And okay, then this, what I'm writing here is not really a clause. And the only thing that you need to do afterwards is you need to take this constraint and actually turn it into clauses that the SAT solver understands. So there's some technical part behind this, which actually takes this PB constraint and turns it into clauses. Okay, and so this sort of ends my explanation for this dominance rule. Maybe a natural question to ask. So we've talked about performance all day. Would be, does this work well in practice? So is this efficient? Yes, sorry.
Yeah, I have a question about the constraint that you introduced when you apply dominance to break the symmetry, right?
Yes. So
okay, what the constraint is saying is after applying sigma, so if I apply sigma, then the order doesn't reduce, if I understand correctly.
Yes.
And unless there's some sort of connection between the order and the symmetry, I don't really see the argument why you couldn't have this situation, right? So you have a symmetry, and the orbit goes in some sequence in the ordering where it goes alternatingly up and down, right? I don't know if you follow my argument. My point is, how do you ensure that symmetry breaker gives you a unique item, so a unique assignment for the orbit?
So I think just adding these constraints here, you don't necessarily have a unique smallest.
Oh, okay. So it's just like you're maybe throwing away some assignments, but in principle, you're not ensuring unique.
No.
Oh, okay. So sorry, I misunderstood that.
Yeah, this would be complete symmetry breaking, where you actually make sure that once you've added all of the clauses, there's actually only one left.
Oh, okay.
But this is usually not done when you are just speeding up a subsolver. This is usually done, for example, in generation problems, where you only want the isomorph-free graphs.
Yeah, sorry, I thought that these two things were the same.
No. Because usually for like isomorph-freeness, this becomes much more expensive.
Okay.
You need to. These are probably also. This would also not be the right way of doing this.
Okay. Thanks.
Okay. Well, question: does this work well in practice? So we've talked about proof logging and checking performance all day. I've heard 10% or something is the goal, and so this is Satsuma without proof logging on pigeonhole principle. This is Satsuma with proof logging, and this is the proof checking, and I think this is more than 10%, and this is more than x10. So there's some asymptotic problem here. And okay, I just want to briefly go over some recent work that we did to try and get a hold of this this logging and checking performance. So, well, why does this happen? Where does this gap come from? Well, it's that modern symmetry detection and breaking empirically usually runs in linear time, and well, the ordering that I've showed you earlier, so this exponential sum here, if you think about it for a second, this is not linear size. So this, even if you encode this in binary, this will take roughly n bits, and if you have n of those, then you will have a encoding size that is roughly quadratic in the number of variables of the ordering. And now we have this asymptotic gap between linear runtime of the symmetry detection and breaking and quadratic runtime or quadratic size of our proof. It gets even worse when you think about actually computing things with these big integers in the end. So probably checking is worse than n squared. Now, what we did to fix this was to actually enrich the proof system with the ability to express these orderings more efficiently using auxiliary variables. So you can introduce variables to mean that the strings are equal up to a certain point. So if we define the Lex order of two strings using auxiliary variables, we can do this more efficiently by first saying, okay, let's compare the first position of the string. Then we have a variable, which means, well, the two strings are equal up to this position. And then we use these auxiliary variables to check, okay, if the string is equal up to a certain point, then we're actually going to compare this point. And this is, of course, much more efficient than these big integers. And in fact, this is linear in the number of variables. But of course, we need these auxiliary variables to be able to encode this so efficiently. And in fact, this is actually very similar to the CNF encoding that we use to actually express these symmetry breaking constraints. So I could just change the title of the slide and just say this is the encoding that we use to actually express the symmetry breaking constraints. It's exactly the same. Now, the problem, of course, was that VariPB didn't allow these order definitions with auxiliary variables, and it was also not so straightforward to allow this in the proof system. And yeah, so the way we actually fixed this was to split the order into two parts. We called them, I think we called them specification and definition. I'm not sure if this is still the current way we're calling them. And yeah, so the names may be slightly confusing, but the meaning is that we can now define the order as a circuit, and the specification only makes sure that this circuit is evaluated correctly. So we have this these auxiliary variables, and they're basically like gates in a circuit, and the specification only makes sure that given some input to the circuit, these are evaluated correctly, and the definition, it actually imposes the ordering itself. So if the circuit is evaluated correctly, it can use the result of this evaluation to actually impose the ordering. And now, why do we split this into these two parts? Well, so that we can assume the specification to be always true. So the specification can go into the premises of our proof rule, and this basically just means if the circuit is evaluated correctly, then things follow. Now, this is the formal definition, and I just want to show you that for our new proof rule, the specification part here goes into the premises, and the actual imposing of the order goes into what we actually want to prove, not in the second part because it's a proof by contradiction, but this is not so important. The important thing is if you do it that way and you're slightly careful, the arguments work just like before. So the correctness of the dominance rule can be argued in the same way, but now you have these auxiliary variables that you can use to define this ordering. And so we implemented these changes in VeryPB and also in the formally verified CakePB checker, and also the appropriate proof logging in Satsuma. And yeah, there are lots of delicate details going into the proof system and also into the proof logging. So it's actually fairly complicated, and I'm going to talk about this in a second. But importantly, if you look at the proof size and the running time, the order can now be encoded in the size of the order, and each symmetry breaking constraint, so if phi is the corresponding symmetry, can be encoded linearly in the support size of the symmetry, which is precisely the correct size, because this is the support is basically the encoding size of the symmetry. So the logging is in a sense perfect because it precisely matches the running time and the encoding size of the involved objects, which is nice. Now, there's a slight caveat here, which is that the checking time is slightly higher. So checking each of these symmetry breaking constraints is not in the size of the support, but in the size of the order, and there's a slight mismatch here still. Okay, when we ran quite a few benchmarks to test the logging and checking performance, and maybe to just give the take-home message. The take-home message is that the logging is basically fixed. You can improve the constant still, but asymptotically it's fine. So the logging is good, but in the checking you can still start to observe this asymptotic gap. And so these are crafted benchmarks. In the crafted benchmarks with lots of symmetries. The top row here you can see the logging performance. The orange line is without logging. The brown line is with the old style of logging, and the red line is with the new style of logging. And for example, here is the pigeonhole principle. You can see that the old one starts to time out at some point, and the red one is fine. Yes?
Is it VeryPB or PB oxide?
This is PB oxide. This is the Rust implementation. And yeah, the checking, you can also see large improvements in the checking time, but still there is an asymptotic gap between the logging and the checking. Okay, we also ran this on sub-competition instances. So we took all of the symmetric instances from 2020 to 2024. This is just running symmetries and no subsolvers involved. And you can see here that we can log all of them. So this is not really a problem. The checking still has a gap to the logging, but we also made big improvements in the checking. So the PB oxide improved from the dark green line to the light green line, and CakePB improved from the dark purple line to the light purple line. Now, one thing to be mentioned here is that so we actually also improved this dark green line to before. So because we were using the newer PB oxide implementation, we also sort of improved the old style of checking by quite a bit. Because we actually went back to older experiments and we saw that instances that used to time out with the old logging now worked. So yeah, actually we made it harder for ourselves to show the improvement. Yes?
Did you detect bugs in Satsuma once you added this?
No bugs.
It's not entirely true. We
No, we found lots of bugs in the proof log.
Yeah.
But none in the no. Yeah, so it's of course bug free.
It could be a fuzzing project.
Yeah, if you find bugs, send them to me. I'm happy. I was to be honest, I was slightly disappointed by this because I thought that, well, we are adding this proof logging. What do I get out of it? I was hoping to fix bugs and to gain insights into the algorithm and all of this, but yeah, it just worked.
Okay. A massive ego boost.
Yeah. Okay, so some remaining challenges. Here are some of the obvious challenges. Always want to go faster, so we can still prove constants in the logging, but this would basically amount to writing more efficient methods to actually write the files, which is sort of boring. And we could also tune specific cases in the proofs, which could also improve the checking times. And yeah, maybe the bigger issue is that there's still this asymptotic gap between logging and checking. But of course, I think there's some diminishing returns because we've improved the checking quite a bit. We improve it further now. Of course, we will gain less probably by doing this. Okay, maybe I have some other challenges. Maybe and of course, this is static symmetry backing. Is still open to apply this to dynamic techniques and see what you can prove using dynamic techniques. Okay, maybe more obvious or more important to me personally is that, well, there's sort of this promise with proof logging that we can generate proofs with just a couple of print statements. I actually went back to the code and I counted the number of print statements, and it's actually 246 print statements just for the symmetry logging. And just to give you a perspective, the code that actually uses the constraints is about 50 lines. So there's a massive gap between the complexity of the producing the constraints code and the actual proof logging code. So the proof logging is now roughly 1,000 lines and is really, really involved. And so this promise is more like generate proofs with just a couple hundred print statements. So it's really involved. And I don't want to, I mean, this was a massive effort to produce this, to get this efficient and nice. But I think there's also some problems attached to this. Namely, I may want to change the algorithm slightly and may want to tune it a little bit differently. And then you need to go back and basically redo certain things in the proof logging. And I think it's also important to think about the simplicity and try to simplify things slightly. Okay. Another thing is, so this is maybe a slight nitpick, of what's actually certified. And this is not just a symmetry backing problem, this is also in many other sub-techniques, but what are we actually certifying? Well, we're certifying that adding the constraints is sound. What are we not certifying? That the constraints are actually breaking any symmetries. So we don't actually know whether what we're adding to the solver is actually doing anything useful. We could be producing garbage that doesn't make it wrong, but also doesn't help. But of course, this would totally never happen. But I think when you think about bugging perspective, this is actually quite important to check this. To be actually sure that your symmetry vector is doing symmetry.
Do you ever try to, I mean, if you have a satisfiable assignment, you could just try to go and see if you could apply some symmetry here, right?
Yes, but of course the symmetry backing is also not complete, so you would expect this to still
you don't expect it to always work, but you could check that you would expect that it works at least sometimes, right? If it never happens, then it's probably wrong.
Yes. I think the important part here, I think the way you catch this is also with performance regression tests, that you actually check that when you use proof logging, you're still improving performance or something. Of course, it still doesn't prove this, but
what you need to do is model counting, because by breaking symmetries, you should just reduce the number of solutions.
Yes.
Well, I mean, it doesn't work to a non-center, but vision all it won't work, right? But
yes, yeah, but as a check, you can do this. Yeah. Yes.
What do you actually mean by actually breaking any symmetries? Like, this is an unsatisfiability proof, so it has no models.
Yes.
So what is yours?
No, but even if it did have models, that's what you can do, right? You can take a
Yes.
highly satisfiable, I guess empirically you take n pins and n holes, and then you randomly sample a bunch of satisfying solutions, or you do something slightly more interesting.
Yeah. I mean, this
And then you just do symmetry breaking and you check that some of these solutions now go bad. That's still kind of not really solving your problem.
Yeah.
But it would be some kind of circumstantial evidence that you're not doing complete garbage.
Yes. I think this is also not something that you would necessarily always do when you run the SAT solver, because if you run symmetry breaking plus SAT solver, you do care about this. You do care about that the answer is correct, right? But for debugging purposes, I think something that checks this is actually quite important. Okay. Then, in summary, we can prove the correctness of these Lex order constraints using the dominance rule invariably. And with the recent work we did, we can also do this fairly efficiently. We have very fast logging, and we have also fairly fast checking that works up to quite a large scale, I would say. So actually the logging overhead is negligible, and yeah, there are some challenges remaining regarding the checking time, what is actually certified, and maybe also some slightly simpler proofs or simpler methods of doing this. And yeah, so the code is of course available. So the auxiliary variables code is not in this repository yet, hopefully very soon. But yeah, that's it from me. Thank you very much.
If I'm interested, so it's slightly unrelated, but if I'm interested in dynamic symmetry breaking, how easy would it be to use your tool to just extract the symmetries and not do the constraints?
I mean, okay. I wouldn't actually know what the point would be, because detecting the symmetries given a formula is quite simple. You just model this graph, and then you run the tool.
I don't want to write the graph library, so
Yes,
I
then
would
you
rather have a tool that detects the symmetries for me.
Yes, then you go into this repository and you steal the code that builds the graph, and then you're there. Right? Yes, but what I said earlier about dynamic symmetry breaking, I think a lot of dynamic symmetry breaking literature gets some things wrong, namely that dynamic symmetry breaking tends to be expensive, and there's actually a lot of symmetry. Most symmetry cases are actually easy to handle. So I think some of these cases you always want to handle statically, like this row symmetry. Also, if you MIP solvers have very advanced symmetry handling. They have a combination of static and dynamic techniques. And for example, row symmetry they handle statically. They don't go into the dynamic techniques. So actually, it's important to weed out some cases before the dynamic handling technique, which is not usually done in SAT. Yeah, there are some papers, but they don't do row symmetry first. Most of the time. They do? Well,
You don't have to do it. You can get by with doing dynamic symmetry fairly efficiently, and I say fairly because we're still testing, without having to do any previous static elimination ahead of time.
I don't think this is true at the scale of SAT, because the problem is if you do dynamic handling, you always do stabilizers.
Yeah.
You apply Schreier-Sims, and if you don't apply Schreier-Sims, your stabilizers are too bad.
Yep.
And I mean, all of the cases that I mentioned here are symmetric actions. Symmetric actions are worst case for Schreier-Sims. And I think at the scale of these, I mean, the pigeonhole formulas is a symmetric action over ungodly amount of variables. You cannot plug this into the Schreier-Sims algorithm, I think.
should try it. It works for SIP. I'm not giving stuff away for tomorrow, but it works for SIP.
We're using Wi-Fi as input.
We are.
I don't think it would work for stuff like this. Yes.
So in the morning we had this scenario where you might be able to fix some variables in your instance that without loss in reality this is always false, and then suddenly a symmetry would arise.
Yes.
Do you think what you've done so far could you run it as some kind of in-processing tool where you maybe look at the formula plus any, I don't know, variables fixed to false at this point, or?
Yes. Yeah, I think it's a very interesting question. I mean, I would call this local symmetries of like a reduced formula or something. I don't know. I think there's a lot that you can still do without doing this. So I think there's still a lot of room for improvement just doing static symmetry breaking, actually, because I don't think we understand many of the groups well or symmetry breaking constraints for the groups well. So I still think there's a lot to do before going to local symmetries.
So maybe I don't know what you mean by local symmetries. So there are two different ways I could see of doing this. So maybe let me ask about both. The first would be if you just globally, the formula was not symmetric because there was some stray variable, but at some point you just realize that, oh, this variable is false. Now you plug this and you simplify the formula, and now it's like globally, now you have a symmetry.
Yes.
Okay. This is one thing you can do. Another thing that you could potentially do, which I don't know if MIP solvers do, is like maybe you've done a few decisions and you're somewhere, some way down in your search tree, and there, given your bounds so far, now you're symmetric. Is that what you mean by local symmetry?
Yes, this is what I mean by local symmetries.
And would MIP solvers do this? Do you know?
For this, I'm not sure. I'm sure there's a paper trying it in that, but I don't know if you run skip in default mode when that does it. This I don't know.
But in general, like if I fire up Satsuma on a 1 million variables formula, like how running time of Satsuma on a more like normal laptop, are we talking 1 second, 10 seconds, 100 seconds?
This really depends. Like the size barely correlates with the runtime sometimes.
Oh,
but the average runtime on the sub-competition set over all instances is 10 seconds. But I think you could tune it differently, get the same benefits.
But that kind of suggests that if we have a 1 hour sub-competition timeout, you could afford to run it at least a few times during the search.
Yes, yeah. But I think as an in-processing rule makes probably the most sense. I would assume, but I don't know. I think you wouldn't even necessarily need to recompute symmetries. You could also try to add just more constraints over time. To use the original symmetries that you had in the beginning, but just add more symmetry breaking constraints if you realize, oh, I probably need more symmetry breaking, and then just try to get a few more nice generators.
How do you handle variable elimination? So if the set solver eliminates variables, so you mean you could just incrementally add the new clauses?
Yeah, I'm not sure. The variable elimination could ruin it, yes.
Yeah. It's not, at least not clear to me that you can just do incremental checks at least, because also strengthening, right? If you strengthen a clause and shorten it, then it can change how symmetries work.
Yes.
Unless we go into the mode where you fully applied symmetries, the transformation symmetry preserved.
Yes, yeah. Which probably has downsides.
Yes.
Yes, but I think in principle there's a lot of things that could still be tried. It probably makes sense. Yes.
On slide 26, 27, you said you extended the VeryPB proof system.
Yes.
And how much more is there now? How much of an extension is that?
I think this is hard for me to answer.
In terms of what? Of the proof system?
Yes, so far as I understood it,
if I have this knowledge base of my constraints, I have some derivation steps, but let's ignore them for now. And I have one line that says 0 is greater or equal to 1. And then I could run an IP solver and get on the knowledge base and also get that it's unsatisfiable, right? And does this still apply for this kind of specification that I have a circuit and plug it to other variables?
I think I don't quite understand this.
Is not part of these circuits don't live in your constraint database. They're just part of what rules you allow.
Yes, they're very restricted. They're only part of the orders, and only when you prove things about the orders, then like these are really introduced, and then they are directly defined by like the by the rest of the variables.
But even before, I mean, Lex order. This is slightly weird, but even before like this new work, you had lexicographic order with this exponential sum. You don't find this in your proof anywhere. This lexicographic order exponential encoding only kicks in when you're doing dominance-based reasoning. Then you have to argue that, oh right, I want to do this remapping, I have to respect the order. So it's only it only shows up at the proof code, but it never shows up in your constraint database.
All right, just a very basic question. So this is part of the 3.0 format. Yes, the auxiliary variables in the order are the.
Yes.
Yeah. Is this, just because I've not kept track, is this published moment?
No.
No.
Well, there's a SAT competition technical documentation.
Yeah, there's the spec, but in terms of like the soundness of this,
No, but the
not written up at this point.
no, but I think you could probably infer this from the sub-competition documentation. It follows exactly the same arguments as the standard dominance rule, but you add this extra step of, okay, we can correctly assign these auxiliary variables, and then it's the normal argument again. I think. Hopefully very soon published.
Yeah, your 1,000 print statements.
Yes.
If we were to put proof logging into say CP or subgraph isomorphism, how many of the 1,000 print statements that we read would we have in common with your 1,000 print statements?
Yeah, probably a lot, because a lot of these are actually defining the order and proving the transitivity proof and the Beats probably knows.
Well, I mean, so I guess in the in SAP solver, you're not proving the transitivity of your order defined by some circuits. That's about half of it, and the other half is saying that the if we have this symmetry breaking constraint, then we indeed decrease the order under our witness, and that I also don't directly see how you would, why that would show up in your CP solver. So I think the main thing that we would have in common is the definition of the circuit, but it's not a very complicated circuit. This is maybe 20 lines of 200. So I think that's, yeah, as long as you're not doing advanced symmetry breaking and talking it in this way, there would not be so much in common.
Well, if we potentially want to do advanced symmetry breaking, because the issue for us is we're generating these big Lex constraints over CP variables, so we're paying a AA exponential cost, and using auxiliary variables, we could cut this down, I think. Because in CP terms, we're sort of generating A is less than B, or A is equal to B, and B is less than C, or. And right now, we turn this into one massive order over everything.
So
Smart table constraint in the order.
yeah, I mean I expect that so the transitivity proof and the reflexivity proof would carry over. The in the when you use the dominance rule, then you're very crucially using that sort of the constraint that you're deriving by dominance is just kind of another way to encode that your order is decreasing, or actually it's negation. So but that I don't really see how you would have that in your CP application.
Yeah, I mean, the main question is, are we going to write these 1,000 print statements again ourselves? Or are we going to put these 1,000 print statements into a library, let's call it?
Yeah, I think especially for the reflexivity, well, the reflexivity proof still falls, but the transitivity proof, it would make a lot of sense to put it in some kind of library.
Okay, yeah.
So I think we do have we have now reached the end of the formal program, so we could continue
just stop the recording.
discussing. But wait, so exactly any final questions that we should have on the recording before we announce Markus's presentation officially closed? Going once, going twice.